Hello, today we'll present the overview of the first experiment of IC engine. And I'm the first presenter, Mingun Park. Our team consists of Caitlin, Ben, and me. This is today's contents. I will present the objective of this experiment, models overview, and calibration. Then, Ben will present data visualization and 4 flywheel versus 1 flywheel result. Lastly, Caitlin will present work energy analysis for flywheel system, future steps, and conclusion. The overall objective of this experiment is to determine system parameters and controls for a newly developed engine. In the first week, we calibrate the torque sensor and perform the work energy analysis of the motor without head to minimize the effect of air. Also, we obtain the flywheel's inertia and a piston's friction effect. The overview of the test system looks like this. The engine is in the green box. In the first week, we removed the head to minimize the effect of air. This will be attached in the second and third weeks. We used 1 flywheel and 4 flywheels in this test for comparison. A motor was used to rotate the engine, and a force transducer measures the motor's torque to the engine. The calibration was done by Yorkbit using voltage and torque measurement. The torque was calculated by multiplying mass and the distance from the mass to the rotation axis. The mass of each weight was 0.2261 kg. We collected data from 10 points, twice for each number of weights, from 0 to 4. We got a gain of 0.13268, a torque offset of 0.11753, and a voltage offset of 0.8858. Voltage offset was determined by the fact that the regression line must pass through the point 0.0.
This is one example graph of the piston position versus the angular position. The movement of the piston was approximated to be a sinusoidal wave, with its maximum at the measured position of top dead center and its minimum at the measured position of bottom dead center. This is useful for our overall goals because we can easily characterize each stroke of the cycle with knowledge of the piston location. This is a graph of the angular velocity versus the angular position for the 0.6 input voltage and 4 flywheels. The graph was used to find when the motor reaches a steady state, and we could use this on the torque versus angular position graph. This is a graph of the torque of the motor versus the angular position for one tested motor RPM. On the left portion of the graph, the motor is accelerating. On the right portion of the graph, the motor is at steady state. This is useful for our overall goals because we can calculate the work done by the motor while it's accelerating and while it's at steady state. The results for running the engine with 4 flywheels and 1 flywheel attached to it at 3 different RPMs each. The frictional work is not constant with the motor RPM. The data for 1 flywheel shows a positive correlation between RPM and frictional torque. The calculated value of the flywheel moment of inertia is about 0.005 kilogram meters squared. There's a large discrepancy between the measured inertias. This discrepancy may come from the variation in motor torque with angular position, even in steady state. The closest measure of inertia was from 0.6 volts and 4 flywheels, while the other measurements are much smaller than the calculated value. We assume that piston moment of inertia was approximately 0 for these calculations, but our data shows that the piston inertia may be significant. When using 1 flywheel instead of 4, the acceleration work of the motor decreased. This is consistent with the theory because a decrease in the inertia of the flywheel leads to a decrease in the work of the motor.
A mathematical model for the flywheel system, shown highlighted in blue, was prepared for the client. This equation can be used to compute the change in kinetic energy necessary to accelerate the flywheel or wheels from rest to a steady state angular velocity. Since the engine head is off during this entire stage of analysis, the work done due to the air is assumed to be zero since there is no air pressure when the flywheel system is open. Additionally, the work done by the piston, which causes the velocity of the flywheels to oscillate slightly within the steady-state region, is assumed to be negligible to simplify the analysis. In this model, A represents the initial displacement of the flywheel, or 0 degrees, and B and C are the angular displacement at which the steady-state velocity begins and when data collection ends, respectively. The total work done, or change in kinetic energy from A to C, is equivalent to the change in kinetic energy from points A to B, since the flywheels maintain a constant velocity after B. The overall change in energy is found by summing the work due to friction in the bearings and work of the motor in stage 1. No additional work is done during stage 2 when the flywheel moves at a steady speed. At the beginning of each lap period, the torque sensor will need to be calibrated to account for the unknown mass of the moment arm. Week 1 was spent analyzing the flywheel system with the engine head off to determine the frictional torque and flywheel inertia. During week 2, the same angular displacement, motor torque, and angular velocity data will be collected for the system with the head on, where the only work done by the air is from the air pressure due to the air inside the engine at the time the data is collected. In week 3, this same procedure will be repeated with the exception of air being injected into the engine to produce a greater work due to air term. Each week, air propagation analysis will be performed to determine the uncertainty of each of the work terms. Ultimately, the flywheel data will be used to prepare a report for the client detailing the mechanical properties of the IC engine and the uncertainty of the model outputs during the full 4-stroke cycle of the engine. The system parameters which produced a flywheel moment of inertia closest to the theoretical value were an input voltage of 0.6 volts and 4 flywheels attached to the motor. During weeks 2 and 3, these recommended parameters will be used for the IC engine to study the system's effectiveness at modeling the full 4-stroke cycle of the IC engine.